Welcome to this lesson on the Centre-Tapped Full-Wave Rectifier. We will begin with the need for full-wave rectification, examine the transformer and the two alternating diode current paths, and then develop the important performance results from first principles. The derivations include average value, RMS value, ripple factor, rectification efficiency, transformer utilization factor, and peak inverse voltage. By the end of the lesson, you should be able to explain the operation of the center-tapped circuit, trace both conduction paths, and interpret the load waveform. You should also be able to derive average and RMS values, ripple factor, rectification efficiency, transformer utilization factor, and the peak inverse voltage requirement of each diode. A half-wave rectifier supplies the load only during one half of the source cycle. A full-wave rectifier uses both halves. The current through the load therefore has the same direction throughout the full 360-degree cycle, with one output pulse every half cycle. This doubles the ripple frequency and improves the use of the transformer and filter. The transformer secondary is divided into two equal half windings by the center tap. If the upper end is positive with respect to the center tap, the lower end is negative by the same amount. We define Vm as the peak voltage of one half secondary, measured from an end to the center tap. The complete end-to-end secondary peak is therefore 2 Vm. The anode of D1 connects to the upper end of the secondary, and the anode of D2 connects to the lower end. Their cathodes join at the positive output node. The load returns to the center tap. This arrangement lets one diode conduct on each source half cycle while keeping load current in the same direction. During the positive half cycle, the upper end of the secondary is positive with respect to the center tap. D1 is forward biased and D2 is reverse biased. Current flows through the upper half winding, D1, and the load, returning through the center tap. The ideal load voltage is Vm sin theta. During the negative half cycle, the transformer polarities reverse. The lower end becomes positive, so D2 conducts and D1 blocks. Current now flows through the lower half winding, D2, and the load. Although the source polarity has reversed, the current through the load still has the same direction. Hence the output equals Vm times the absolute value of sin theta. Combining the two conduction intervals gives an absolute sine waveform. Its repetition period is pi radians rather than 2 pi radians. Consequently, the ripple frequency is twice the supply frequency. With a 50 Hz supply, the pulsating output repeats at 100 Hz. We first derive the standard waveform factors with ideal diodes. This keeps the shape mathematics clear. In a practical circuit, one diode drop appears in the conducting path, and forward resistance reduces the peak current. We will include forward resistance explicitly in the efficiency expression. For every average and RMS calculation, we use the complete 2 pi electrical cycle. On the first half cycle the current is Im sin theta. On the second, it is minus Im sin theta, which is positive because sin theta is negative there. Equivalently, the current is Im times the absolute value of sin theta. Average current is the integral of the instantaneous current over a complete cycle, divided by the cycle length, 2 pi. Because the two positive half-sine pulses are identical, we may integrate the first pulse and multiply by 2. This symmetry is the key difference from the half-wave derivation. The integral of sin theta is minus cosine theta. Evaluating from 0 to pi gives 2. Therefore the average load current is 2 Im divided by pi, or approximately 0.637 times the peak current. This is twice the half-wave average for the same peak. For a purely resistive load, the instantaneous voltage and current are proportional. Multiplying the average current by RL gives the average load voltage. Since Vm equals Im RL in the ideal circuit, VDC is 2 Vm divided by pi, again 0.637 of the peak. RMS current is defined as the square root of the mean of the squared current. Squaring removes the sign difference between the two half cycles. We therefore integrate sine squared over the complete 2 pi interval and then take the square root. The integral of sine squared over a complete cycle is pi. Substitution leaves the square root of 1/2. Hence the RMS load current is Im divided by square root 2, or 0.707 Im. Full wave rectification changes the polarity, but not the RMS magnitude of a sinusoid. The RMS load voltage is Vm divided by square root 2. The form factor is RMS divided by average. Substituting the two results gives pi divided by 2 square root 2, equal to 1.111. This ratio leads directly to the ripple factor result. A pulsating output contains a DC component and an AC ripple component. Their RMS squares add. Solving for the RMS ripple current and dividing by the DC current gives the ripple factor. A smaller ripple factor means an output closer to pure DC before filtering. Substituting IRMS equal to Im over square root 2, and IDC equal to 2 Im over pi, cancels the peak current. The ripple factor is the square root of pi squared over 8 minus 1. Numerically this is 0.482, or 48.2%. Rectification efficiency is useful DC load power divided by the AC power supplied to the rectifier circuit. The useful power is IDC squared RL. The input power is based on RMS current and includes the load resistance plus the forward resistance of the conducting diode. Substitution cancels Im squared. Rearranging gives 8 over pi squared, multiplied by the fraction RL over RL plus RF. In the ideal limit, RF approaches 0, and the maximum rectification efficiency is 0.812, or 81.2%. Transformer utilization factor, or TUF, is the DC load power divided by the transformer volt-ampere rating. For the center-tapped secondary, each half winding carries current for only one half cycle. We must therefore calculate the RMS current in each half winding and combine the two half winding VA contributions. Consider one half of the transformer secondary. It carries a sine current only during its conducting half cycle and zero current during the other half. Its RMS current over the complete cycle is therefore Im over 2. The RMS voltage of that half winding is Vm over square root 2. The two equal half windings contribute equal volt-ampere values. Adding them gives Vm Im over square root 2. The DC load power is VDC times IDC. Substituting both average values gives 4 Vm Im divided by pi squared. Dividing DC output power by the total secondary volt-ampere rating cancels Vm and Im. The resulting transformer utilization factor is 4 square root 2 divided by pi squared, or 0.573. Thus about 57.3% of the secondary VA capability appears as DC load power under the standard ideal convention. At the positive peak, D1 conducts and places the output node near plus Vm. At the same instant, the anode of D2 is at minus Vm. The reverse voltage across D2 is therefore plus Vm minus Vm, equal to 2 Vm. The same reasoning applies to D1 on the opposite half cycle. The diode repetitive peak reverse voltage rating must exceed 2 Vm, with a suitable design margin for supply variation and transients. The current rating, surge capability, power dissipation, junction temperature, and reverse recovery requirement must also be checked. Consider an ideal center-tapped rectifier in which each half secondary supplies 12 volts RMS to a 100 ohm load. The half secondary peak is 16.97 volts, giving a peak current of 169.7 mA. The average output is 10.8 volts and 108 mA. The RMS output is 12 volts and 120 mA. The ripple factor, ideal maximum efficiency, and TUF retain their waveform values. Each diode must withstand a PIV of 33.94 volts before margin. This table gathers the ideal results. The average value is 2 over pi times the peak. The RMS value is 1 over square root 2 times the peak. Ripple factor is 0.482, maximum efficiency is 81.2%, secondary TUF is 0.573, ripple frequency is twice the supply frequency, and diode PIV is twice the half-secondary peak. A center-tapped full-wave rectifier uses two diodes alternately, with the center tap as the return path. It produces a positive load pulse during each half cycle. The average is 0.637 of the half-secondary peak, the RMS value is 0.707 of the peak, and the ideal efficiency reaches 81.2%. Remember that each diode must withstand twice the half-secondary peak voltage,